Hello bachos, welcome to the class. Today we're tackling a very interesting topic from Unit 2, Electrostatic Potential and Capacitance, which is energy stored in a capacitor. I will explain it so simply that you will lose all fear of this topic and remember it for your exams and for life. And every point will be perfectly exam safe. Okay, let's dive into this.
So let's start with a simple question to get you thinking.
Just think about it. How can a tiny little battery create such a bright, powerful flash in just a fraction of a second? Well, this is a fantastic example of what we're about to learn, storing energy and then releasing it very, very fast. And the secret hero behind this magic is the capacitor.
To understand this, let's forget about electricity for a moment and think of something really simple.
This is the core idea. Imagine you are pumping air into a bicycle tire. The first few pumps are so easy, nah? But as the tire gets fuller and the pressure builds up, you have to push much, much harder to get more air in. Well, charging a capacitor is exactly like that.
So look at how this works. The first bit of charge you put on the plate, super easy, no problem. But as the plate gets more and more crowded with charge, it starts pushing back. This pushback is what we call voltage. So to push the last bit of charge onto the plate, the battery has to do the maximum amount of work against this repulsion. Now, this work that the battery does, it doesn't just disappear. In physics, work done against an electric force gets stored as potential energy. Buckle simple. Okay, now let's see how we write this idea down in a formula that will get you full marks in your exam.
This is the main formula you must remember. The potential energy stored, which we write as U, is equal to half times the capacitance, C, times the square of the potential difference, V. एकदम इसको note कर लो in your notebook.
Now, the crucial point here is to be smart when solving problems. We already know the basic relation Q equals CV, right? So using this, we can actually write the energy formula in two other ways. So depending on the problem, you can use these other two forms as well. If they give you charge Q and capacitance C, use the second one. If they give you Q and V, use the third one. Just pick the right one to get the answer quickly.
Now, for those of you aiming for top marks, let's quickly see where this formula actually comes from. It's very logical. डरने की कोई बात नहीं है.
And this brilliantly illustrates how we build up from a tiny bit of work to the final expression. We start by thinking about the small amount of work, dW, needed to move a tiny charge, dQ. Then, to get the total work, we just add up all these tiny bits of work, from the very beginning when the charge was 0, all the way up to the final charge, Q. This process of adding up all the tiny parts is what we call integration. And when we do that, we get our final formula for the total energy stored.
Okay, let's apply what we just learned to a very simple numerical problem, just like you might see in an exam. Chalo, try this. They've given us C and V. So which formula are we going to use? Obvious, right? U is equal to half CV square.
The answer is 0.01 joules. See, you just put the values in the formula, that's 1/2, times 2 into 10 to the power of minus 6 farads times 100 squared. It's a simple calculation. But now you might be thinking,
Hey, 0.01 joules, that's a tiny amount of energy. And you're right. But remember our camera flash? The secret is not the amount of energy, but the speed at which it's released. A capacitor can dump all of this energy in maybe 1,000th of a second. And energy released per unit time is power. That's what creates that massive, powerful flash.
all right, let's move on and see how we can avoid a very common mistake that many students make, which can cost them precious marks. Pay close attention to this part. So many students forget the 1/2 factor. They just write energy equals QV. Why? Because they're thinking, oh, work done is just charge times voltage, so W equals QV. But they forget that the voltage was not constant while the capacitor was charging. It grew from 0 all the way to V. So we have to use the average voltage, which is 0 plus V divided by 2. And that gives us V over 2. That's where the 1/2 comes from. Here's a simple way to remember this for life. If you were to plot a graph of voltage versus charge as the capacitor gets charged, you would get a straight line that forms a nice triangle. The energy stored is simply the area under this graph. And what is the area of a triangle? It's half into base into height. In our case, that's 1/2 times Q times V. This is a memory trick you will never forget. So, let's quickly summarize the most important points from this topic.
These are the absolute essentials you need to take away from this explainer. First, the energy isn't in the metal plates. It's actually stored in the electric field between the plates. Second, remember the three main forms of our golden formula.
And of course, never ever forget that 1/2 factor from the area of the triangle. Today.
And listen, this isn't just a dead-end topic. This concept of stored energy is the foundation for future chapters on oscillations and waves. It's like the stored fuel that powers all kinds of amazing things, making it super important. I hope this was useful.